The generation ship drifts into outer space after leaving its home system, entering a region dominated by near-vacuum conditions, where matter becomes extremely sparse and light spreads without obstruction across vast distances. The environment outside the vessel is not empty in a perfect sense, but contains scattered particles, primarily hydrogen atoms, with occasional helium nuclei, and trace heavier elements distributed unevenly through the galactic medium. These particles are separated by distances so large that collisions are rare, yet over extended timescales. They still interact with the hull, producing gradual changes in surface structure and composition. The generation ship experiences this environment as a continuous low-density flow of particles and radiation, where the absence of atmospheric shielding exposes every external surface to direct cosmic conditions. Temperature in this region is not perceived as air temperature but as equilibrium between absorbed solar radiation and emitted infrared energy, allowing the hull to oscillate slowly between heating and cooling, depending on orientation relative to distant stars. Over long periods of travel, the vessel moves through regions of slightly different density, where interstellar clouds may increase particle interactions, creating subtle variations in erosion rates across its outer plating. The radiation environment consists of high-energy particles originating from distant supernovae and active stellar regions. These particles travel nearly at the speed of light and pass through space, continuously forming a persistent background influence on all matter. The outer hull material absorbs a portion of this energy, while allowing some to penetrate deeper layers, where it contributes to slow structural changes in molecular bonds and crystalline lattice stability. Microscopic impact from dust grains occur intermittently, producing localized heating and vaporization events that gradually sand down exposed surfaces over thousands of years. These processes are individually minor but collectively significant. The absence of atmospheric drag means that these impacts occur at full relative velocity determined by the ship trajectory and galactic motion, making even microscopic particles capable of transferring measurable energy to structural layers. Over time, the combination of radiation exposure and particle impacts leads to gradual degradation of protective coatings, requiring internal systems to compensate through redundancy and adaptive maintenance cycles. Magnetic fields also extend across vast regions, shaping the motion of charged particles, which spiral along invisible field lines and contribute to uneven distribution of energetic flux around the vessel. These magnetic influences are weak compared to planetary fields, yet across millions of kilometers they accumulate into structured patterns that affect radiation, shielding performance and particle penetration probabilities. The generation ship must maintain internal stability despite this variability, relying on engineered redundancy rather than environmental predictability, since no surrounding atmosphere can buffer external changes. Small fluctuations in particle density can occur when the vessel passes through remnants of supernova ejecta or diffuse molecular clouds where hydrogen density rises slightly above background levels. In such regions, the rate of atomic collisions increases modestly, creating additional thermal load on external systems and subtle changes in erosion patterns. The ship does not experience these transitions as abrupt events, but as slow gradients unfolding over years or decades, reflecting the immense scale of interstellar travel. Cosmic radiation exposure remains one of the most persistent influences acting on both structural materials and electronic systems inside protective layers. High-energy particles can generate secondary cascades that penetrate deeper than the initial impact. These cascades produce gradual accumulation of defects in semiconductor components and slowly alter material properties in ways that require continuous correction and system recalibration. Despite the harshness of this environment, it remains consistent across large regions of space, meaning that once adaptive systems are tuned to local conditions, they can maintain stability for extended durations. The outer transit region therefore becomes a domain where survival depends less on immediate resistance and more on long-term adaptation to cumulative microscopic change. Time itself functions as the primary shaping force with every passing year, adding incremental stress and requiring continuous adjustment of structural and operational systems. The absence of nearby planetary bodies also removes gravitational stabilizers that typically influence trajectory in more crowded systems, leaving the ship to follow a smoother but less adjustable path, determined primarily by its initial velocity and distant gravitational gradients. These gradients arise from the combined mass of the galaxy, including stars, stellar remnants, and dark matter distributions, which subtly influence motion even across interstellar distances. Over extremely long timescales, these influences can slightly alter the ship trajectory, but the changes remain gradual and predictable within broad statistical ranges. The external environment therefore remains stable in its instability, meaning that while conditions are harsh, they do not fluctuate rapidly enough to create sudden catastrophic transitions under normal circumstances. This allows long-duration engineering systems to operate with predictable maintenance schedules, even as microscopic damage accumulates continuously across all exposed surfaces. The outer transit region therefore represents a slow, acting but persistent field of physical interaction, where radiation particles, dust grains, and magnetic influences combine into a constant background pressure on engineered systems. The materials used in external plating are selected for resistance to sputtering and radiation-induced displacement, where atoms are gradually knocked out of lattice positions over extended exposure. This slow atomic rearrangement leads to measurable changes in hardness and conductivity, requiring occasional resurfacing using internal maintenance systems. Even with such protection, the outer layers accumulate a record of their journey, written not in visible marks alone but in microscopic defects distributed across atomic scales. The cumulative nature of these processes defines the true character of deep space transit, where change occurs continuously but rarely appears dramatic. The generation ship moves deeper into the interstellar medium, where the density of matter increases slightly compared to the near void of open galactic space, though it remains extremely thin by any planetary standard. This region contains diffuse hydrogen atoms, ionized plasma, and microscopic dust grains dispersed across enormous volumes. The hydrogen exists mostly in atomic form rather than molecular clusters, separated by distances so large that each atom effectively travels alone until it interacts with radiation or magnetic fields. The ship passes through this medium steadily, and the surrounding environment changes only in gradual shifts across vast distances rather than sharp boundaries. The interstellar medium is structured into broad regions shaped by past stellar activity. Remnants of ancient supernovae form faint shells of gas that expand and mix with surrounding space over millions of years. Within these shells, density may be slightly higher, and temperature may vary depending on how recently the gas was heated by shock waves. The generation ship crosses such regions without direct sensory awareness, yet its external sensors record subtle increases in particle flux and changes in radiation background levels. These variations remain small but persistent, influencing long-term exposure of outer materials. The hydrogen atoms in this region carry minimal kinetic energy, yet their collective presence defines the structure of the medium. Some regions are warmer and ionized, meaning electrons are separated from nuclei and move freely as plasma. In these zones, electromagnetic fields play a stronger role guiding charged particles along curved paths that trace the invisible architecture of galactic magnetism. The ship interacts with this plasma through its own induced magnetic fields, which deflect charged particles away from critical systems and reduce direct surface impacts. Dust grains within the interstellar medium are composed of silicates, carbon compounds, and frozen ices in colder regions. These grains are microscopic, but significantly more massive than individual atoms, and when they collide with the ship's outer layers at high relative velocities, they transfer concentrated energy into very small impact zones. Over long periods, these impacts cause localized erosion, sputtering, and gradual alteration of surface chemistry. Protective shielding layers are designed to absorb and disperse this energy, converting it into heat that is radiated away into space. Radiation in this region includes not only distant stellar light, but also energetic particles known as cosmic rays. These particles originate from extreme astrophysical events such as supernovae and neutron star interactions. They travel across the galaxy nearly unimpeded, carrying energies far greater than typical atomic interactions. When they strike the ship, they penetrate deeply, sometimes reaching inner structural layers despite multiple shielding barriers. Their interactions produce secondary particles that cascade through materials, creating chains of ionization events that slowly degrade electronic components and alter molecular structures. The interstellar medium is not uniform, and the ship encounters variations in density that influence how quickly these processes occur. In denser regions, even by a small margin, the frequency of particle interactions increases, leading to slightly higher thermal loads and more frequent microscopic impacts. In more rarefied regions, these effects diminish, but radiation exposure remains relatively constant, because cosmic rays pass through all regions with little obstruction. This consistency makes radiation one of the most persistent long-term stresses in deep space travel. Thermal conditions in the interstellar medium are determined not by air temperature but by radiation balance and particle energy distribution. The ship's external surfaces absorb energy from particle collisions and radiation absorption, then release it slowly as infrared emission. This balance creates a stable but dynamic thermal environment where small fluctuations reflect changes in surrounding particle density or orientation relative to distant stars. Over centuries, these small variations accumulate into long-term thermal cycling effects on structural materials. Magnetic fields in the interstellar medium arise from the motion of ionized gas and the remnants of stellar magnetic structures. These fields are extremely weak compared to planetary fields, but extend across vast distances, forming large-scale patterns that guide charged particle motion. The generation ship's own systems interact with these fields, sometimes aligning with them, and sometimes resisting them depending on propulsion and shielding configurations. This interaction influences how charged particles approach the vessel, creating uneven distributions of radiation exposure across its hull. Inside the ship, isolation from the external environment becomes increasingly important as exposure time accumulates. Even with strong shielding, small quantities of radiation penetrate into internal systems, affecting sensitive electronics and biological materials. The effects are not immediate but accumulate slowly, requiring continuous monitoring and correction. Over long durations, this leads to gradual adaptation of both materials and maintenance strategies, as systems are redesigned to tolerate the cumulative effects of deep space exposure. The interstellar medium also contains traces of molecular clouds colder and denser regions, where hydrogen atoms combine into molecules and dust accumulates more heavily. When the ship passes near the outer edges of such clouds, it experiences slight increases in particle density and changes in radiation scattering patterns. These transitions are not abrupt, but extend over vast distances, producing slow environmental gradients that persist for years. Within these regions, the balance between heating and cooling shifts, slightly requiring adjustments in thermal management systems. Despite these variations, the overall environment remains fundamentally sparse. The distance between particles ensures that collisions are rare, and most interactions occur only through high-energy processes or electromagnetic influence. This creates a setting where change is continuous but extremely slow, and where survival depends on long-term resilience rather than immediate adaptation. The ship continues its journey through this diffuse medium, gradually accumulating the physical record of every particle encounter across its outer layers. The generation ship continues its journey deeper into the galactic environment, where the dominant influence becomes the persistent background of high-energy radiation, known as the galactic cosmic ray field. This radiation is composed of charged particles that originate from distant astrophysical events, such as supernova explosions, pulsar activity, and energetic processes near compact stellar remnants. These particles travel through space at velocities close to the speed of light and maintain their energy across vast interstellar distances, making them one of the most consistent energetic features of deep space. Unlike local radiation sources that weaken with distance, cosmic rays are distributed across the galaxy in a relatively uniform manner with only gradual variations depending on proximity to active stellar regions. The generation ship experiences this radiation as a continuous, invisible flux that passes through all external layers and interacts with shielding materials at the atomic scale. Each high-energy particle carries enough momentum to disrupt molecular bonds when it collides with matter, producing cascades of secondary particles that spread energy through small volumes of material. These cascades are known as particle showers, where a single cosmic ray interaction generates multiple lower-energy particles that propagate through the structure. Within shielding layers, these secondary interactions are gradually absorbed, but a fraction of energy always penetrates deeper reaching sensitive systems. Over long periods, this results in the slow accumulation of radiation-induced defects in structural materials and electronic components. Semiconductor lattices are particularly sensitive as displaced atoms and ionization events can alter conductivity and introduce random fluctuations in signal behavior. The intensity of cosmic ray exposure is not constant, but varies with the ship's position relative to large-scale galactic structures. Regions near dense star clusters or remnants of supernova activity show slightly elevated flux levels, while more isolated regions exhibit marginally lower intensity. However, even in the lowest exposure zones, the background radiation remains significant enough to require continuous shielding and system redundancy. The absence of a protective planetary magnetic field or thick atmospheric layer means that the ship relies entirely on engineered barriers to mitigate exposure. Magnetic fields within the galaxy influence the trajectories of charged cosmic rays, bending their paths into spirals and arcs that follow the structure of interstellar magnetic lines. These fields are extremely weak compared to those found near planets or stars, but across galactic distances they become significant in shaping particle distribution. As a result, the radiation environment encountered by the ship is not entirely random, but exhibits subtle directional patterns that shift slowly over time as the vessel moves through different magnetic regions. The energy spectrum of cosmic rays spans a wide range from relatively low-energy particles that are easily absorbed by outer shielding layers to extremely high-energy particles capable of penetrating deep into dense materials. The highest energy events are rare but carry disproportionately large effects when they occur. A single such particle can create extensive ionization tracks through multiple layers of shielding, leaving behind microscopic damage pathways that accumulate over time. These tracks are not visible at macroscopic scale, but represent permanent alterations in material structure. The generation ship's shielding systems are designed in multiple layers, each optimized for different types of radiation interaction. Outer layers focus on dispersing energy from particle collisions, while inner layers are designed to absorb secondary radiation and prevent penetration into habitable zones. Between these layers, magnetic field generators redirect charged particles, reducing the probability of direct impact on critical systems. Despite these measures, no shielding configuration can completely eliminate exposure, only reduce it to manageable levels. Over long durations, this persistent radiation environment influences not only physical materials, but also operational cycles. Electronic systems require periodic recalibration to account for gradual drift in component behavior caused by accumulated radiation damage. Memory storage systems employ redundancy and error correction to maintain data integrity in the presence of random bit flips induced by high-energy particle interactions. These corrections occur continuously in the background, forming an invisible maintenance process that sustains system stability. Biological systems within the ship are also affected by this radiation field, though they are protected by additional shielding layers and controlled habitats. Even so, small amounts of radiation penetrate into living environments, causing low levels of DNA damage that must be repaired by biological processes. Over long timescales, this creates a steady background rate of cellular repair activity, influencing biological aging and adaptation mechanisms within the closed ecosystem. The cosmic ray environment also interacts with the ship's external hull in ways that produce faint secondary emissions. When high-energy particles strike shielding materials, they generate brief bursts of electromagnetic radiation and particle emissions that propagate outward and inward simultaneously. These secondary emissions contribute to the overall radiation environment and must also be accounted for in shielding design. The interplay between primary cosmic rays and secondary cascades creates a complex layered radiation field around the vessel. As the ship continues its trajectory through the galaxy, it does not encounter dramatic changes in radiation conditions, but instead experiences gradual shifts in intensity and composition. These shifts reflect the broader structure of the galaxy itself, where regions of star formation, stellar death, and interstellar voids create a slowly varying background of energetic particles. The ship's systems remain in constant adaptation to this environment, maintaining stability through continuous adjustment rather than static resistance. The persistence of cosmic radiation defines this region of deep space as one of constant energetic interaction at microscopic scales. Every moment of travel adds incremental exposure, and every layer of shielding participates in a continuous process of energy absorption and redistribution. Over time, this creates a cumulative record of passage through the galaxy, written not in visible markings but in subtle atomic rearrangements embedded within the structure of the vessel. The generation ship advances along a slow and stable trajectory, shaped by the combined gravitational influence of the galaxy. In this region, motion is not determined by nearby planets or stars, but by the cumulative mass of distant structures distributed across vast distances. Each star cloud of gas and compact stellar remnant contributes a faint gravitational pull, and together these influences form a large-scale field that guides the ship's path over time. The motion appears smooth and continuous, yet it is the result of countless overlapping gravitational contributions that change gradually as the vessel moves through different regions of space. The ship's trajectory is established long before departure based on calculated orbital mechanics that account for known stellar positions and galactic mass distribution. Once in deep space, adjustments become rare and subtle, relying on minimal propulsion corrections that compensate for long-term drift rather than immediate course changes. Without nearby massive bodies to create strong gravitational swings, the path remains relatively stable, shaped mostly by slow curvature in the galactic potential field. This gravitational field is not uniform. It varies depending on the density of stars and dark matter concentrations in different regions of the galaxy. As the ship moves through areas with slightly higher stellar density, the combined gravitational pull increases, causing minor but measurable changes in velocity and direction. These changes occur over long timescales, unfolding gradually across centuries, and are often too small to be detected without continuous long-term observation. Dark matter, though not directly observable, contributes significantly to the overall gravitational structure of the galaxy. Its distribution is inferred from rotational dynamics of galaxies and gravitational lensing effects observed in astrophysics. In the region of the ship's travel, dark matter is thought to form a diffuse halo that extends far beyond visible structures. Its presence subtly influences the ship's motion, adding a smooth background curvature to its trajectory that cannot be attributed solely to visible matter. As the ship moves, it passes through regions shaped by past stellar evolution. Some areas contain remnants of supernova explosions where mass was violently redistributed into surrounding space. These regions have slightly altered gravitational characteristics due to the redistribution of matter into expanding shells and diffuse clouds. The ship's trajectory responds to these variations with gentle deviations, reflecting the long-term memory of stellar activity embedded in the structure of the galaxy. Gravitational interactions in this environment are cumulative rather than instantaneous. Unlike planetary systems where strong local forces dominate interstellar travel, involves extremely weak but persistent influences. Each small gravitational pull adds incrementally to the ship's velocity vector, slowly altering its direction over time. The effect is subtle but becomes significant when considered across millions of years, shaping the overall architecture of interstellar navigation. The absence of strong gravitational wells means that the ship does not experience orbital capture or sudden acceleration events unless it approaches a dense stellar region. Instead, its motion resembles a long, gentle arc through space guided by the large-scale structure of the galaxy. This type of trajectory requires careful initial planning and continuous monitoring, as small deviations can accumulate into large positional shifts over extended durations. Inside the vessel, inertial stability systems compensate for minor gravitational variations. These systems maintain internal equilibrium, so that living environments remain unaffected by slow external changes in velocity or direction. Without such stabilization, even gradual shifts in motion could produce long-term stress on structural frameworks and human habitats. The systems operate continuously, adjusting microaccelerations to maintain a consistent, artificial gravitational environment within rotating or accelerated sections of the ship. The interaction between external gravitational fields and internal artificial gravity systems creates a layered dynamic where two distinct forms of acceleration coexist. External gravitational influences shape the ship's overall path through space, while internal systems maintain localized stability for biological and mechanical continuity. These two systems operate independently, but must remain carefully synchronized to prevent structural stress accumulation over time. As the ship moves farther from its origin, the gravitational influence of its home star becomes negligible. The vessel is no longer bound to any single stellar system, and instead responds only to the broader galactic field. This transition marks a shift from localized orbital dynamics to fully interstellar motion, where no single body dominates the trajectory. The ship effectively becomes part of the galaxy's large-scale flow of mass and energy, Occasional encounters with minor gravitational perturbations occur when the ship passes near diffuse gas clouds or isolated stellar remnants. These interactions are weak but can slightly alter the trajectory if sustained over long periods. Navigation systems continuously account for these influences, adjusting thrust vectors in small increments to maintain desired course alignment. These adjustments are minimal but essential for ensuring long-term navigational accuracy across interstellar distances. The gravitational environment also influences the distribution of interstellar matter around the ship. Dust and gas respond to the same large-scale fields, forming subtle gradients that the vessel passes through. These gradients do not create resistance in the traditional sense, but contribute to variations in particle density encountered by the hull. Over time, this adds another layer of environmental interaction that complements radiation and particle exposure. Despite the complexity of these overlapping influences, the ship's motion remains remarkably stable on human timescales. Changes that would be dramatic in planetary environments unfold so slowly in interstellar space that they are perceived only through long-term measurement. The galaxy provides a vast but gentle guiding structure, allowing the vessel to travel across immense distances without abrupt transitions or destabilizing forces. This gravitational continuity defines the mid-scale environment of deep space travel, where motion is neither chaotic nor fixed, but shaped by persistent low-intensity forces distributed across the entire galaxy. The ship moves through this field as part of a larger system of mass in motion, gradually tracing a path defined by the invisible architecture of cosmic gravity. The generation ship now travels through a region where the external environment begins to interact more directly with the physical structure of the vessel, not through large-scale forces, but through continuous microscopic contact with interstellar particles. The outer hull becomes the first boundary where the environment leaves a permanent physical record as dust grains and high-speed particles collide with the surface at extreme relative velocities. These impacts occur infrequently on human timescales, yet across centuries they form a constant background process of erosion and modification. Micrometeoroids in this environment are extremely small fragments of rock metal and frozen compounds that drift through interstellar space. Their origins trace back to ancient planetary collisions, stellar outflows, and disrupted cometary bodies that were scattered across the galaxy. When these particles strike the hull, they do not behave like ordinary low-speed impacts. Instead, their velocities are so high that even microscopic grains carry enough energy to vaporize both themselves and a small portion of the surface upon contact. This produces tiny craters and ejecta patterns that slowly roughen the exterior over time. The distribution of these impacts is not uniform. Some regions of space contain slightly higher densities of debris due to past supernova events or the gravitational disruption of planetary systems. As the ship passes through such regions, the rate of surface impacts increases marginally, creating subtle variations in erosion patterns across different sections of the hull. Over long durations, these variations accumulate into uneven surface textures that reflect the ship's trajectory through the galaxy. The outermost layer of the vessel is engineered specifically to absorb and dissipate the energy of these collisions. It is composed of materials designed to withstand repeated high-energy particle strikes without catastrophic failure. When an impact occurs, the energy is distributed across a small region of material, converting kinetic energy into heat and structural deformation at microscopic scales. Some of this energy is radiated away almost immediately, while the rest is absorbed into deeper layers where it gradually disperses. Repeated impacts lead to a process known as sputtering, where individual atoms are ejected from the surface due to momentum transfer from incoming particles. Over extremely long timescales, this results in measurable mass loss from exposed surfaces. Although the rate is extremely slow, the cumulative effect over thousands or millions of years becomes significant enough to require consideration in structural design. Protective coatings are periodically renewed by internal maintenance systems that rebuild or reinforce external layers from within. Beneath the outermost surface, structural materials experience secondary effect from impact energy. Shock waves propagate through crystalline lattices, creating dislocations and defects that alter mechanical properties such as hardness and elasticity. These changes occur at a microscopic level and do not immediately compromise structural integrity, but they gradually shift the long-term behavior of materials. Engineers account for this by selecting alloys and composites that can tolerate long-term defect accumulation without losing essential strength. Thermal effects accompany each impact event. When a particle collides with the hull, the energy is converted partly into heat, creating localized temperature spikes that dissipate rapidly into surrounding material. Although each event is extremely small, the continuous nature of impacts means that the outer surface exists in a constant state of low-level thermal fluctuation. Over time, this contributes to slow diffusion processes within the material structure, subtly altering chemical bonds and lattice arrangements. The generation ship also encounters dust grains that are significantly larger than atomic-scale particles, but still microscopic by macroscopic standards. These grains can penetrate shallow layers of shielding, embedding themselves into outer coatings or creating shallow impact channels. Their chemical composition varies depending on their origin, ranging from silicate-based minerals to carbon-rich compounds formed in ancient stellar environments. When embedded into the hull, they may react chemically with surface materials under radiation exposure, creating new compound structures not originally present in the vessel's construction. Radiation and particle impacts often interact in complex ways. A dust grain struck by a cosmic ray can fragment into smaller particles, each carrying energy into different layers of material. This creates a cascading effect where a single event leads to multiple secondary interactions distributed across microscopic regions. Over long periods, these interactions contribute to a gradual homogenization of surface chemistry, blending original material distinctions into more uniform compositions shaped by exposure rather than design. The structural integrity of the hull depends on redundancy rather than absolute resistance. Multiple layers of protective material ensure that even if one layer is compromised by repeated impacts, deeper layers continue to provide protection. Between these layers, vacuum gaps and energy-dissipating structures reduce the transmission of mechanical shock. This layered design ensures that damage remains localized rather than propagating through the entire structure. Despite this protection, the outer hull gradually evolves as a record of environmental exposure. Each impact, each atom displaced, and each thermal fluctuation contributes to a long-term transformation that reflects the conditions of deep space travel. The vessel does not remain static in form, but slowly adapts through accumulation of microscopic changes that cannot be reversed individually, but can be managed collectively through maintenance cycles. As the ship continues its journey, it passes through regions where dust density varies slightly due to remnants of past astrophysical events. These variations produce small changes in impact frequency, but the overall process remains continuous and unavoidable. The hull becomes a chronicle of passage through space, not through visible markings alone, but through a dense network of atomic-scale modifications distributed across every exposed surface. This outer layer represents the first and most persistent interface between the generation ship and the universe beyond it. It absorbs the full complexity of interstellar conditions and translates them into gradual physical change, ensuring that the vessel's structure carries within it the accumulated history of every particle encountered along its path. The generation ship now moves into a stage of deep space travel, where shielding systems become the primary determinant of long-term survival, rather than the external environment itself. The outer hull continues to absorb impacts and radiation, but beneath it lies a carefully engineered sequence of protective barriers designed to manage energy transfer before it can reach inhabited regions. These shielding layers are not static walls but dynamic systems that respond to continuous particle bombardment and radiation exposure over extended periods. The first major shielding layer beneath the external hull is composed of high-density composite materials designed to slow and fragment incoming particles. When high-energy cosmic rays or micrometeoroid fragments penetrate the outer surface, this layer spreads their energy across a wider area, reducing localized damage. The process is not one of complete absorption, but controlled dispersion, where kinetic and radiative energy is gradually reduced through repeated interactions with atomic structures. As particles pass through this layer, they undergo repeated collisions with nuclei in the material, losing energy at each interaction. These collisions produce secondary particles that travel in multiple directions, creating a dispersed energy field rather than a single focused path of destruction. The shielding is designed so that these secondary particles are less harmful than the original incoming radiation, allowing subsequent layers to manage reduced energy levels more effectively. Beyond the initial dispersal layer lies a radiation attenuation zone composed of materials selected for their ability to interact with high-energy photons and charged particles. In this region, electromagnetic interactions become dominant, and particles lose energy through ionization processes. Electrons are stripped from atoms within the shielding material, creating localized charge imbalances that are quickly neutralized by conductive pathways embedded throughout the structure. These pathways prevent buildup of static charge that could otherwise destabilize sensitive systems. Magnetic field generators are integrated within and around these shielding layers, creating controlled fields that influence the trajectory of charged particles. When cosmic rays or ionized particles enter these regions, their paths are bent into curved trajectories, increasing the probability of collision with shielding material rather than penetration into deeper layers. This magnetic deflection does not eliminate radiation, but redistributes it across a broader surface area, reducing concentration of energy at any single point. The effectiveness of magnetic shielding depends on particle energy and charge. Neutral particles such as neutrons produced in secondary interactions are not affected by magnetic fields and can penetrate deeper into the structure. These neutrons eventually interact with atomic nuclei in the shielding layers, producing further secondary radiation. To manage this, the ship includes neutron-absorbing materials enriched with elements that have high capture cross-sections, allowing them to absorb or slow neutrons before they reach critical systems. Thermal shielding is integrated alongside radiation protection systems because every interaction between particles and matter produces heat. Over long durations, even low levels of energy deposition can lead to significant thermal buildup if not properly managed. Heat pipes and radiative panels distribute this energy across large surface areas, where it is emitted as infrared radiation into space. This process maintains internal thermal stability despite continuous external energy input. The shielding architecture is not uniform across the entire vessel. Regions closer to habitation modules receive additional layers of protection, while outer sections focus more heavily on structural resilience and energy dispersion. This gradient approach ensures that mass and shielding resources are allocated efficiently without compromising safety. Over time, these systems are adjusted based on observed radiation patterns and long-term exposure data collected from sensors embedded throughout the hull. Radiation exposure within shielding layers also leads to gradual material transformation. High-energy particles displace atoms from their lattice positions, creating defects that accumulate over time. These defects can alter mechanical properties such as density, conductivity, and structural rigidity. To counteract this, some shielding materials are designed with self-healing properties, where atomic rearrangement over time reduces defect concentration, or where maintenance systems actively repair damaged regions using deposited material layers. Secondary particle cascades remain one of the most challenging aspects of shielding design. When a high-energy cosmic ray enters the outer layers, it can generate a chain reaction of particle production, including gamma rays, electrons, and neutrons. Each of these secondary particles carries reduced but still significant energy, requiring multiple layers of attenuation. The shielding system is therefore not designed to stop a single event, but to gradually reduce energy across many stages until it reaches harmless levels. The internal boundary of the shielding system marks the transition from external hazard management to controlled environmental stability. Beyond this point, radiation levels are significantly reduced but not entirely eliminated. Sensitive biological and electronic systems still experience low levels of background radiation, requiring additional localized protection. This includes biological shielding for living habitats, where water, organic materials, and specialized polymers are used to further absorb residual radiation. Long-term exposure to radiation also affects the shielding system itself. Materials gradually accumulate damage that cannot be fully reversed, leading to slow changes in structural properties over decades and centuries. This necessitates continuous monitoring and periodic reinforcement, where new shielding layers are added, or existing ones are modified to maintain performance standards. The ship effectively becomes a self-maintaining structure that evolves in response to its environment. The interaction between shielding systems and external radiation creates a dynamic equilibrium. Energy is constantly entering the system, being redistributed and eventually emitted or absorbed. This balance is never perfectly stable, but fluctuates within controlled limits, ensuring that no single component experiences overwhelming stress. The design philosophy relies on redundancy and gradual degradation rather than absolute protection, acknowledging the inevitability of long-term environmental exposure. As the generation ship continues its journey, the shielding layers form an increasingly complex record of accumulated interactions. Each layer reflects a different stage of energy reduction, from initial high-energy impacts to low-level residual radiation. Together, they represent a multi-stage barrier that allows sustained survival in an environment defined by persistent energetic activity and slow but unending physical transformation. The generation ship now operates within a regime where thermal regulation becomes a central factor in maintaining long-term structural and biological stability. The external environment of deep space does not provide a conventional temperature, but instead defines a radiative balance in which the vessel continuously exchanges energy with the surrounding vacuum. Heat generated internally from life support systems, electronic operations, and mechanical movement must be managed carefully to prevent gradual accumulation that could destabilize internal conditions over extended time. The outer layers of the vessel are engineered not only for radiation and particle shielding, but also as part of a large-scale thermal interface. These layers absorb energy from high-velocity particle impacts and radiation interactions, temporarily storing it in molecular vibrations before gradually releasing it into space as infrared radiation. This emission process is slow and continuous, allowing the vessel to maintain equilibrium between internal heat production and external energy loss. Within the thermal regulation system, heat is transported away from localized sources through a network of conductive structures and fluid-based circulation pathways. These systems rely on controlled movement of thermal energy, through materials that are designed to efficiently distribute heat across large surface areas. The goal is not to eliminate heat, but to prevent concentration, ensuring that no region of the ship experiences sustained thermal stress that could weaken structural integrity or disrupt sensitive systems. Radiative panels form a critical part of this thermal management architecture. These surfaces are oriented and adjusted to maximize energy emission into deep space where background radiation levels are extremely low and heat can be efficiently dissipated. The effectiveness of these panels depends on their exposure to unobstructed space, meaning their positioning must avoid interference from other structural components or accumulated dust and debris on the outer hull. Over long periods, maintenance systems periodically clean and adjust these surfaces to preserve thermal efficiency. The internal thermal environment of the ship is divided into controlled zones, each with specific temperature requirements depending on function. Living habitats require stable conditions that support biological processes, while computational and mechanical systems may operate within broader thermal ranges. This zoning ensures that heat generated in one region does not propagate unchecked into areas where even small fluctuations could lead to instability or reduced efficiency. Heat generation within the vessel is continuous and multifaceted. Biological processes produce metabolic heat. Electronic systems generate waste heat through electrical resistance, and mechanical systems contribute through friction and motion. Even in highly optimized systems, complete elimination of waste heat is impossible, making thermal regulation a constant requirement, rather than a periodic adjustment. The accumulation of these small energy outputs over time necessitates continuous redistribution. As the ship travels through different regions of space, external thermal conditions vary slightly due to differences in background radiation and particle density. Although space itself is extremely cold in a physical sense, the presence of radiation fields and particle interactions introduces subtle variations in energy absorption. When the ship passes through regions with higher interstellar density, additional thermal input occurs due to increased particle collisions with the hull requiring adjustments in heat dissipation rates. Thermal inertia plays a significant role in stabilizing the internal environment. Large structural components of the vessel absorb heat slowly and release it over extended periods, smoothing out short-term fluctuations. This prevents rapid temperature changes that could stress materials or disrupt biological systems. The balance between rapid heat generation and slow thermal release creates a buffered environment, where changes occur gradually rather than abruptly. Material selection within the thermal system is critical for long-term performance. Different layers of the ship are composed of substances with specific thermal conductivities and heat capacities allowing for controlled movement of energy. Some materials are designed to store heat temporarily, while others facilitate rapid transfer or emission. This combination creates a layered thermal architecture where energy flows in a controlled gradient from internal sources to external radiative surfaces. Thermal regulation is closely linked with radiation shielding systems, as both involve interaction with high-energy particles. When radiation penetrates shielding layers, it deposits energy that must be managed as heat. This coupling means that changes in radiation intensity directly influence thermal load, creating a dynamic relationship between external cosmic conditions and internal temperature control. The ship's systems continuously adjust to this relationship to maintain equilibrium. Over long durations, thermal cycling produces gradual changes in material properties. Repeated heating and cooling cause expansion and contraction at microscopic scales, which can lead to slow fatigue in structural components. Although these changes occur very gradually, they accumulate over centuries, requiring periodic reinforcement and material renewal. Maintenance systems address this by monitoring stress patterns and applying corrective structural updates where needed. The radiative emission of heat into space is ultimately the only mechanism by which the ship can permanently remove excess energy. This process depends on the temperature difference between the vessel and the surrounding environment, which remains effectively near absolute zero in deep space. Because of this large gradient, even small increases in internal temperature result in efficient outward radiation, allowing the system to maintain long-term stability as long as emission surfaces remain functional. Despite the efficiency of this system, thermal balance is never perfectly static. Continuous internal activity ensures that small fluctuations are always present, requiring constant adjustment. The ship exists in a state of managed thermal flow, rather than fixed equilibrium where energy is always in motion between generation, redistribution, and emission. This dynamic balance defines the thermal character of long-duration deep space habitation. As the vessel continues its journey, thermal regulation becomes not just a system of control, but a defining feature of its existence in space. Every structure, material, and process contributes to the ongoing management of energy, ensuring that internal conditions remain stable despite the persistent and unavoidable generation of heat. The ship therefore maintains its livable environment through continuous distributed and adaptive thermal exchange with the surrounding vacuum of space. The generation ship now operates within a structural regime where mechanical integrity depends on the distribution of forces across an immense and continuously active framework. Unlike planetary structures that rely on static support from gravity, this vessel must maintain its form entirely through engineered internal balance. Every section of the structure participates in carrying load, transmitting stress and stabilizing motion across distances that span kilometers within the habitat system. The central structural frame acts as the primary backbone of the vessel, forming a continuous network of load-bearing elements that extend through habitation zones, engineering compartments, and propulsion-adjacent regions. This frame does not function as a single rigid body, but as a distributed lattice that allows controlled flexibility. The purpose of this flexibility is to absorb gradual mechanical stress without allowing localized failure to propagate through the entire system. Mechanical forces within the ship arise from multiple sources. Rotational motion used to simulate gravity generates continuous outward acceleration that places tensile stress on structural components. Internal movement of fluids, shifting of mass within agricultural systems, and operation of large-scale machinery all contribute additional dynamic forces. Even small variations in mass distribution can create oscillations that must be dampened through structural design rather than external stabilization. The structural system responds to these forces through controlled deformation at microscopic and macroscopic scales. Materials used in the framework are selected for their ability to distribute stress across broad regions rather than concentrating it at single points. When force is applied, energy is transmitted through interconnected pathways that allow gradual dissipation rather than abrupt failure. This distributed response prevents the formation of weak points that could compromise structural continuity over long durations. Vibration damping systems are embedded throughout the framework to manage oscillatory motion. These systems convert mechanical vibration into thermal energy, or redistribute it across larger masses where it becomes negligible. Over time, even minor vibrations generated by routine operations can accumulate into structural fatigue if not properly managed. The damping systems ensure that these effects remain within safe thresholds by continuously absorbing and redistributing energy. The rotational habitat system introduces one of the most significant structural loads within the vessel. As the ship rotates to generate artificial gravity, Every connected structure experiences outward force proportional to its distance from the axis of rotation. This creates a gradient of stress that must be carefully balanced through reinforcement and geometric design. The structural frame is therefore arranged to align with these gradients, allowing forces to flow naturally through designated load paths. Connections between structural elements are engineered to allow controlled movement without loss of integrity. Instead of rigid joints that resist all deformation, many connections are designed to flex slightly under load, absorbing stress through small reversible changes in shape. This flexibility reduces the likelihood of fracture under long-term cyclic loading, which would otherwise accumulate over centuries of rotation and operational activity. Thermal expansion also contributes to structural stress. As materials heat and cool due to internal processes and external radiation exposure, they expand and contract at different rates, depending on composition. These variations create internal tensions that must be accommodated by the structural framework. Expansion joints and adaptive connectors allow different sections of the ship to move independently within controlled limits, preventing the buildup of destructive internal stress. The interaction between structural mechanics and radiation exposure further complicates long-term integrity. High-energy particles gradually alter material properties at the atomic level, introducing defects that can affect strength and elasticity. Over extended periods, these changes influence how materials respond to mechanical stress. Structural design accounts for this by incorporating redundancy and allowing for gradual reinforcement of affected regions. Load distribution within the ship is not static but evolves over time. As mass is relocated for operational purposes such as resource processing, habitat adjustments, or system upgrades, the structural load paths shift accordingly. The framework is designed to adapt to these changes through modular construction, allowing sections to be reinforced or reconfigured without disrupting overall stability. Large-scale structural stability depends on the integration of multiple subsystems working together. Mechanical frameworks, thermal management systems, and radiation shielding all contribute indirectly to structural integrity by influencing material behavior and energy distribution. This interdependence means that structural health cannot be evaluated in isolation, but must be understood as part of a complex interconnected system. Over long durations, microscopic changes accumulate within structural materials due to continuous stress cycling. Even when loads remain within safe limits, repeated application over centuries leads to gradual fatigue at the atomic scale. This process does not cause immediate failure but slowly alters mechanical properties, requiring continuous monitoring and predictive maintenance strategies. Maintenance systems operate throughout the structure, scanning for early signs of stress concentration, deformation, and material degradation. When necessary, localized reinforcement is applied using internal fabrication units that restore or enhance structural capacity. This process ensures that the vessel remains functionally stable despite the inevitable accumulation of mechanical wear. The structural framework ultimately defines the physical identity of the generation ship. It is not a static object, but a continuously maintained system of balance between force motion and material response. Every component contributes to a larger equilibrium that allows the vessel to maintain integrity while moving through an environment where no external support exists. This balance is maintained not through rigidity, but through controlled adaptability, allowing the structure to persist across vast timescales of interstellar travel. The generation ship now enters a phase where artificial gravity becomes the central environmental system shaping human habitation, replacing the natural gravitational conditions that exist near planetary bodies. This artificial gravity is created primarily through controlled rotation, producing a steady outward acceleration that mimics the sensation of weight. Within this rotating structure, every object, fluid, and organism experiences a constant directional force that defines orientation, movement, and long-term physical adaptation. The rotating habitat ring is the largest and most structurally complex component responsible for this effect. It is arranged as a continuous circular structure with living spaces distributed along its inner surface. As the ring rotates, centrifugal acceleration pushes matter outward toward the hull, creating a stable directional force that acts consistently across the entire habitat. This force is not gravity in a physical sense, but produces similar effects on biological and mechanical systems, allowing normal activity to continue in an environment far from any planetary surface. The magnitude of artificial gravity depends on rotation speed and radius. Larger radii allow lower rotational speeds to achieve the same effective gravity, reducing mechanical stress and minimizing physiological side effects associated with motion. The ship's design balances these factors to maintain a stable environment that can support long-term biological function without introducing excessive strain on structural systems or human perception. Within this rotating environment, spatial orientation becomes a constant feature of daily existence. The direction of artificial gravity defines what is perceived as up and down, while the curvature of the habitat subtly influences how motion is experienced across long distances. Even large structures within the ring must be aligned carefully to ensure that weight distribution remains consistent and that no region experiences uneven loading that could distort the artificial gravity field. Fluid behavior within the rotating habitat is strongly influenced by this artificial gravity. Liquids settle along the outer hull, forming stable layers that mimic natural pooling under planetary gravity. This allows for familiar systems of water storage, agriculture, and biological circulation. However, the Coriolis effect introduced by rotation influences the movement of fluids and air currents, creating curved flow patterns that must be accounted for in system design. Ventilation systems and liquid transport networks are engineered to compensate for these predictable but continuous deflections. Human physiology within the rotating habitat adapts to the sustained artificial gravity environment. Musculoskeletal systems respond to constant outward force, maintaining structural integrity through continuous mechanical loading. Over long durations, biological systems adjust to this artificial condition, as if it were natural gravity, although subtle differences remain in fluid distribution and vestibular perception. These differences are managed through controlled environmental stability and gradual adaptation across generations. The structural demands of the rotating habitat are significant because centrifugal forces increase with distance from the rotational axis. This creates a gradient of stress that must be carefully distributed across the supporting framework. Outer regions experience the highest forces, requiring stronger materials and reinforcement, while inner structures near the axis experience reduced loading, but must still maintain alignment and stability within the rotating system. Energy is required to initiate and maintain rotation, but once established, the system remains stable with minimal continuous input. Adjustments are occasionally required to compensate for mass redistribution within the habitat, such as movement of stored resources, population shifts, or changes in operational configuration. These adjustments are small but necessary to prevent long-term imbalance that could affect rotational stability. The interface between the rotating habitat and non-rotating sections of the ship introduces complex mechanical transitions. Bearings, dampers, and isolation systems are used to separate rotating and stationary structures, preventing vibration transfer and mechanical stress accumulation. These interfaces are among the most critical engineering components in the entire vessel, as failure would disrupt the artificial gravity system and compromise habitat stability. Lighting within the rotating habitat is carefully controlled to simulate consistent day-night cycles independent of external space conditions. Since the vessel may travel through regions with varying external light intensity, internal lighting systems provide stable illumination patterns that support biological rhythms. These cycles are synchronized with rotation to reinforce spatial orientation and maintain psychological continuity across generations. The artificial gravity system also influences long-term settlement patterns within the habitat. Over time, infrastructure, agriculture, and living spaces become organized according to the constant directional force, creating layered vertical structures that mirror planetary environments. Waste management, resource distribution, and transportation systems all align with this artificial gravitational gradient, forming a fully self-consistent internal world. Despite its stability, the rotating system introduces long-term mechanical considerations. Continuous rotation generates cyclic stress in structural materials, leading to gradual fatigue over extended periods. This requires ongoing monitoring and maintenance to ensure that microscopic structural changes do not accumulate into larger mechanical weaknesses. The system is therefore not static, but continuously managed to preserve balance and integrity. The artificial gravity environment ultimately defines the human experience aboard the generation ship. It creates a stable, continuous reference frame in which life can proceed in a structured and predictable manner, despite the absence of natural planetary conditions. This engineered gravity field becomes the foundation upon which all biological, mechanical, and social systems are built, sustaining continuity across generations traveling through deep space. The generation ship now operates within a fully enclosed atmospheric system, where the composition, pressure, and circulation of air are entirely maintained by internal engineering rather than any external planetary influence. This atmosphere is a carefully balanced mixture of gases designed to support human respiration, material stability, and biological processes across many generations. It exists as a self-contained environment, continuously monitored and adjusted to prevent drift in composition over long periods of isolation. Oxygen within the system is produced and regulated through a combination of chemical processing, biological regeneration, and controlled electrochemical reactions. Carbon dioxide produced by human respiration and other biological activity is continuously removed through absorption systems and converted back into usable components. These processes form a closed loop where no gas is permanently lost, only transformed and recycled through different stages of the life support infrastructure. Nitrogen acts as the primary inert buffer gas, maintaining stable atmospheric pressure and reducing the risk of rapid combustion or chemical instability. Its role is not directly biological, but structural, providing a stable medium in which oxygen concentration can remain within safe limits. The balance between oxygen, nitrogen, and trace gases is continuously adjusted through sensor networks distributed throughout the habitat, ensuring that even minor deviations are corrected before they accumulate into larger atmospheric changes. Air circulation is maintained through large-scale ventilation systems that move gas through every region of the habitat in controlled patterns. These systems ensure that oxygen distribution remains uniform and that localized accumulation of heat, carbon dioxide, or contaminants does not occur. The movement of air is carefully designed to avoid strong turbulence, while still ensuring complete mixing over time, creating a stable but dynamic atmospheric flow. Within this enclosed system, pressure is maintained at levels similar to planetary environments to support human physiology and structural stability. Pressure variations are minimized through feedback-controlled regulation systems that respond to even small changes in gas volume or temperature. Thermal expansion and contraction of gases are accounted for, continuously preventing pressure drift that could otherwise accumulate over long durations. Contaminant management is a critical aspect of atmospheric control. Microscopic particles generated by material-aware biological processes and industrial activity are continuously filtered from the air. High-efficiency filtration systems remove particulate matter at scales far below human perception, ensuring that long-term accumulation does not affect respiratory health or mechanical systems. Some contaminants are chemically processed and recycled, while others are safely isolated and stored for later disposal or reuse. Biological interaction plays an important role in maintaining atmospheric stability. Plants and microbial systems contribute to oxygen production and carbon dioxide absorption, forming a biological complement to mechanical life support systems. These biological components introduce variability into the system, requiring constant monitoring to ensure that growth rates and metabolic activity remain within controlled limits. The integration of biological and mechanical systems creates a hybrid atmosphere management structure that is both self-regulating and actively controlled. Humidity levels are carefully controlled to maintain comfort and prevent material degradation. Water vapor is continuously cycled through evaporation, condensation, and recovery systems that ensure efficient reuse of water resources. Excess humidity is removed through condensation units, while dry conditions are corrected through controlled vapor release. This balance is essential for both biological health and material preservation within the habitat. Trace gases are monitored at extremely low concentrations because even small deviations can have significant long-term effects on both biological and chemical systems. These gases may originate from industrial processes, biological activity, or slow material breakdown. Specialized sensors detect and analyze these components continuously, allowing for precise regulation of atmospheric chemistry. In some cases, trace gases are intentionally introduced in controlled amounts to support specific biological or chemical functions. Air pressure stability is closely linked to thermal regulation, as temperature changes directly affect gas density and behavior. The atmospheric system is therefore integrated with the ship's thermal management infrastructure, ensuring that heat distribution and gas circulation operate as a unified system. This integration prevents the formation of pressure gradients that could destabilize internal environments over time. In the absence of natural atmospheric exchange with an external environment, the system relies entirely on internal feedback loops. Every change in gas composition, temperature, or pressure is measured, analyzed, and corrected through automated processes that operate continuously. This creates a closed atmospheric ecology where stability depends on constant observation and adjustment rather than passive equilibrium. Over long durations, the atmosphere itself becomes a dynamic record of internal activity. Every biological process, every mechanical operation, and every system adjustment contributes to subtle shifts in gas composition and circulation patterns. These shifts are not harmful when controlled, but represent the ongoing interaction between living systems and engineered infrastructure within a closed environment. The atmospheric system ultimately defines the internal environment of the generation ship as a fully self-contained world. It replaces the natural variability of planetary atmospheres with a precisely controlled and continuously managed system that supports life through sustained balance rather than environmental change. This engineered atmosphere remains stable not because it is static, but because it is constantly maintained in response to the smallest variations across the entire vessel. The generation ship now relies on a fully enclosed water system where every molecule of liquid is continuously tracked, recovered, and reused through tightly controlled cycles. Water in this environment is not a freely replenished resource, but a closed system asset that circulates between biological, mechanical, and chemical processes without external input. Its stability depends on precise balance between consumption, purification, and redistribution across the entire vessel. Water begins its cycle primarily within human and biological systems, where it is used in respiration, metabolism, and cellular function. After passing through biological processes, it becomes part of wastewater streams containing dissolved organic compounds, salts, and microscopic biological residues. These streams are immediately collected through drainage and transport systems designed to prevent any loss into inaccessible regions of the ship. Once collected, water enters a multi-stage purification process. The first stage removes large particulates and biological matter through physical filtration. This step ensures that organic debris and suspended solids do not accumulate or interfere with later processing stages. The filtered water then moves into chemical treatment systems, where dissolved compounds are separated based on molecular structure and reactivity. These processes rely on controlled chemical interactions that isolate contaminants without destroying the water itself. Following chemical treatment, advanced purification systems remove remaining microscopic impurities. These systems often rely on membrane technologies and selective absorption materials that allow water molecules to pass while trapping residual contaminants. The precision of this stage is extremely high, because even trace impurities can accumulate over time in a closed system, potentially affecting both biological health and mechanical performance. Sterilization is an essential step in maintaining long-term water stability. Residual microbial life that survives earlier stages is neutralized using controlled energy exposure or chemical treatment. This ensures that the water remains biologically safe for consumption and reuse. The sterilization process is carefully regulated to avoid altering the chemical composition of the water beyond acceptable limits, preserving its suitability for both biological and industrial use. Once purified, water is redistributed throughout the ship according to demand. Biological systems receive water for consumption and metabolic use. Agricultural modules use it for plant growth and nutrient transport, and industrial systems employ it for cooling, cleaning, and chemical processing. This redistribution is managed through a network of pressurized channels that ensure precise delivery to all required systems. Evaporation and condensation play a central role in maintaining atmospheric and hydrological balance. Water vapor produced by biological and mechanical processes enters the atmosphere and is later recovered through condensation systems embedded within temperature-controlled surfaces. These surfaces are designed to collect vapor efficiently, converting it back into liquid form without significant loss. This continuous phase change cycle ensures that water remains in constant circulation between liquid and gaseous states. Storage within the system is distributed rather than centralized. Water reserves exist in multiple interconnected reservoirs positioned throughout the ship to maintain balance and reduce risk of system-wide loss. These reservoirs also function as thermal buffers, absorbing heat energy due to water's high heat capacity and slowly releasing it to stabilize internal temperature fluctuations. Agricultural systems within the vessel represent one of the largest consumers of water. Plants require controlled irrigation to maintain growth cycles, and hydroponic systems are often used to maximize efficiency by delivering water directly to roots in measured quantities. After use, excess water is collected, filtered, and returned to the cycle, ensuring that no portion of the agricultural system results in permanent water loss. Human consumption represents a smaller but critical component of the water cycle. Drinking hygiene and medical applications require water of extremely high purity. These requirements are met through additional localized purification stages that refine water beyond standard system-wide processing. This ensures that even minor contaminants do not accumulate in biological tissues over time. Industrial processes also rely heavily on water for cooling and chemical reactions. In these systems, water absorbs heat or participates in controlled reactions before being recovered and purified again. The efficiency of recovery is essential because any loss would gradually destabilize the closed system over long durations. As a result, nearly all water is continuously cycled rather than consumed. Leaks or losses within the system are treated as critical failures because even small losses accumulate over generations. Detection systems monitor pressure flow and chemical composition continuously to identify any deviation from expected parameters. When discrepancies are found, automated repair systems isolate affected regions and restore balance through localized intervention. Over time, the water system becomes deeply integrated with every other life support system aboard the ship. It is not an isolated utility, but a central medium connecting biological, atmospheric, thermal, and chemical processes. Its behavior reflects the state of the entire vessel, as changes in consumption or contamination often indicate broader shifts in system activity. The water cycle ultimately functions as a closed ecological loop that sustains life by ensuring continuous transformation rather than replacement. Every molecule is reused countless times across generations, maintaining stability through precision control and continuous feedback. In this system, water becomes not just a resource, but a persistent circulating structure that binds together the living environment of the generation ship. The generation ship now operates with fully enclosed biological production systems, where food is generated through controlled ecosystems rather than external supply chains. These systems are designed to sustain human life over multiple generations by transforming light nutrients and recycled waste into edible biomass within carefully regulated environments. Food production becomes a continuous biological process integrated into the ship's broader closed-loop life support architecture. Agricultural chambers form the foundation of this system, providing controlled environments where plants grow under artificial lighting and precisely regulated atmospheric conditions. Light is supplied at specific wavelengths, optimized for photosynthesis, allowing plants to convert carbon dioxide and water into organic compounds. These chambers are arranged in layered structures to maximize space efficiency, with multiple growth cycles occurring simultaneously across different zones. Soil is largely replaced by hydroponic and aeroponic systems, where nutrients are delivered directly to plant roots through water-based solutions or fine mist distributions. This approach eliminates the variability of natural soil while allowing precise control over nutrient composition. Essential elements such as nitrogen, phosphorus, and potassium are carefully balanced within these solutions to maintain consistent growth rates and prevent long-term depletion. Biological waste recycling is tightly integrated into food production. Organic waste from humans, plants, and microbial systems is processed and broken down into basic chemical components that can be reused as nutrients. This process involves controlled decomposition stages where microbial communities convert complex organic matter into simpler compounds. These compounds are then reintroduced into agricultural systems, closing the nutrient loop and minimizing resource loss. Microbial systems play a central role in maintaining soil-like environments and supporting plant health. These microorganisms assist in nutrient cycling, organic matter breakdown, and disease suppression within controlled environments. Their populations are carefully managed to prevent imbalance, as uncontrolled microbial growth could disrupt agricultural stability. Over long durations, these microbial communities evolve within the closed environment, adapting to the specific conditions of the ship's ecosystem. Protein production is supported not only through plant cultivation, but also through controlled biological systems that include microbial protein synthesis and, in some designs, insect-based or cellular agriculture systems. These systems are highly efficient in converting recycled nutrients into edible biomass, reducing the land or volume requirements compared to traditional agriculture. All production methods are designed to maximize caloric output while minimizing resource input and waste generation. Water use within food production systems is tightly regulated and fully integrated into the ship's water recycling network. Irrigation, nutrient delivery, and humidity control are all part of a unified system where water is continuously recovered and reused. Evaporation from plant surfaces contributes to atmospheric humidity, which is later condensed and returned to circulation, ensuring no net loss of water through agricultural activity. Energy input for food production is derived from the ship's internal power systems, primarily supporting artificial lighting and environmental regulation. These systems operate on carefully balanced energy budgets to ensure that food production remains sustainable over extremely long durations. Light cycles are optimized not only for plant growth, but also for synchronization with human circadian rhythms, supporting biological stability in a fully artificial environment. Crop selection within the agricultural system is determined by nutritional efficiency, growth speed, and resilience to closed system conditions. Plants that provide high caloric yield with minimal resource input are prioritized, while genetic stability is maintained through controlled breeding or stored genetic libraries. This ensures that food production remains consistent even across many generations despite potential biological drift in isolated conditions. Storage of harvested food is managed through climate-controlled environments that prevent spoilage and maintain nutritional integrity. Some food is consumed immediately after production, while other portions are processed into long-term storage forms, such as dried fermented or preserved products. These storage methods provide redundancy in case of temporary disruptions in production cycles. The integration of food production with atmospheric and water systems creates a tightly interconnected biological network. Carbon dioxide from respiration supports plant growth, while oxygen produced by plants sustains human life. Waste products from one system become inputs for another, forming a continuous loop that stabilizes both biological and environmental conditions. Over time, agricultural systems become semi-autonomous ecological environments that require careful oversight rather than constant manual control. While engineered systems guide their behavior, biological processes introduce natural variability that must be continuously monitored and adjusted. This balance between control and biological adaptation is essential for long-term sustainability in a closed environment. Food production ultimately becomes more than a supply system. It evolves into a central pillar of ecological stability aboard the generation ship. It links energy, matter, and biological life into a continuous cycle that supports survival across generations. Every harvest, every cycle of growth, and every recycling process contributes to a sustained equilibrium that allows life to persist far from any natural planetary ecosystem. The generation ship now functions as a fully enclosed biological ecosystem, where microbial and human life are deeply interwoven within shared environmental cycles. At this stage of long-duration travel, the stability of life support depends not only on engineered systems but also on the behavior of microscopic organisms that exist throughout air-water surfaces and living bodies. These microbial communities form an invisible but essential layer of biological regulation that sustains the internal balance of the vessel. Human microbiomes are among the most complex components of this system. Each person carries vast populations of bacteria, fungi, and other microorganisms that support digestion, immune function, and metabolic regulation. Within the closed environment of the ship, these microbiomes do not interact with external biodiversity as they would on a planetary surface. Instead, they evolve within a stable but isolated ecological framework, gradually adapting to the specific conditions of artificial life support systems. The stability of these microbial populations is critical. If certain species become dominant or decline excessively, it can affect human health and system-wide biological processes. Continuous monitoring of microbial balance is therefore integrated into medical and environmental systems. Adjustments are made through diet regulation, environmental control, and targeted biological interventions that maintain equilibrium without disrupting the broader ecosystem. Environmental microbiomes exist throughout the ship's infrastructure, particularly in water systems, agricultural chambers, air circulation pathways, and waste processing units. These microbial communities are responsible for breaking down organic matter, recycling nutrients, and maintaining chemical stability across multiple subsystems. Their activity ensures that waste does not accumulate in harmful concentrations and that essential elements are continuously reintroduced into usable forms. In water systems, microorganisms assist in the decomposition of organic contaminants and contribute to the purification cycle. In agricultural environments, they support plant health by facilitating nutrient absorption and protecting against harmful pathogens. In air systems, microbial populations help stabilize trace chemical compounds and contribute to the breakdown of airborne organic particles. Across all systems, they act as distributed processes embedded within the life support network. The interaction between engineered systems and microbial life creates a hybrid ecological structure. Mechanical processes provide stability and control, while biological processes introduce adaptability and self-sustaining transformation. This combination allows the system to remain functional even in the face of gradual changes in environmental conditions or resource distribution. Over long durations, this hybrid structure becomes increasingly interdependent. Within this closed environment, microbial evolution proceeds under highly constrained conditions. Without external genetic input, populations evolve through internal variation and selective pressures imposed by artificial habitats. These pressures include nutrient availability, temperature, stability, radiation exposure, and chemical composition of surrounding systems. Over many generations, this leads to the emergence of microbial strains specifically adapted to the unique environment of the generation ship. Human biological systems are influenced by these evolving microbial populations. Changes in microbial balance can affect digestion efficiency, immune response, and overall physiological stability. As a result, medical systems continuously track microbial composition within human populations to ensure long-term health stability. Interventions are applied when necessary to prevent harmful imbalances or unintended evolutionary drift. Surface microbiomes also develop across structural materials within the ship. These communities inhabit walls, water channels, filtration systems, and agricultural infrastructure. Some are beneficial, contributing to material stability and waste breakdown, while others must be carefully controlled to prevent degradation or contamination. The distinction between useful and harmful microbial activity becomes a central aspect of environmental management. The closed nature of the system means that microbial extinction or overgrowth cannot be easily corrected through external replacement. Instead, stability must be maintained through internal regulation and redundancy. Multiple overlapping microbial populations often perform similar ecological roles, ensuring that if one group declines, others can compensate. This redundancy is essential for maintaining long-term ecological resilience. Energy flow within microbial systems is continuous but slow compared to mechanical systems. Organic matter is broken down, gradually releasing nutrients back into circulation over extended periods. This slow processing ensures stability, but also requires careful balancing to prevent accumulation of intermediate compounds that could disrupt chemical equilibrium. System design therefore integrates microbial processes into broader cycles of water, air, and food production. Radiation exposure in deep space also affects microbial evolution. Although shielded, low levels of radiation still penetrate into biological environments, introducing genetic variation over time. This variation contributes to evolutionary change, but within tightly constrained boundaries defined by environmental stability. The result is a slow, guided form of evolution, shaped by both random mutation and engineered selection pressures. Over long durations, microbial and human systems become inseparable components of a single ecological identity. The ship is no longer simply a machine containing life, but a self-sustaining biological system operating within a mechanical framework. Every biological process contributes to system-wide stability, and every engineered system supports biological continuity. This integration defines the deepest level of ecological stability within the generation ship. Life is maintained not through isolation from biology, but through continuous collaboration with it. Microbial systems, human populations, and engineered infrastructure form a unified network of interdependent processes that sustain each other across generations in a closed and unchanging external environment. The generation ship now enters a stage where long-term survival depends not only on environmental control and biological stability, but on the continuity of human populations across many generations in complete isolation. In this enclosed system, population dynamics become a central factor shaping the future of the vessel as demographic balance, genetic variation, and reproductive patterns gradually define the long-term viability of human life. Population size is maintained within carefully controlled limits to ensure that resource consumption, social stability, and genetic diversity remain in balance. If the population grows too large, it places strain on food production, water recycling, and atmospheric systems. If it becomes too small, genetic diversity declines and increases the risk of inherited disorders. The system therefore requires continuous regulation through social planning, resource distribution, and long-term demographic forecasting. Genetic stability is a critical concern in isolated environments. Without external genetic input, populations are subject to genetic drift, a process in which random changes in gene frequencies accumulate over generations. Over long periods, this can reduce diversity and increase the prevalence of harmful genetic traits. To counteract this, genetic monitoring systems track variation across the population and maintain databases of genetic information to support long-term diversity management. Reproductive patterns are influenced by both biological factors and system-level planning. In a closed environment, reproduction cannot be left entirely to chance without risking imbalance in population structure. Age distribution, genetic compatibility, and resource availability all influence reproductive planning. This creates a controlled demographic structure where population continuity is guided to maintain long-term stability rather than short-term variation. Inheritance of traits within the population occurs under conditions of environmental uniformity. Unlike planetary populations exposed to diverse ecosystems, the ship's inhabitants exist within a stable and highly controlled environment. This reduces external selective pressures, meaning that small genetic variations may persist longer than they would in natural environments. Over time, this can lead to subtle shifts in population characteristics shaped primarily by internal conditions rather than external adaptation. Mutations occur continuously at a low rate due to natural biological processes and residual radiation exposure. Even with shielding background radiation from deep space introduces occasional genetic changes. Most of these mutations are neutral or corrected by biological repair mechanisms, but over many generations a small fraction persists and becomes part of the genetic landscape of the population. These changes contribute to slow evolutionary drift within the isolated system. Medical systems play an essential role in maintaining population health. Continuous monitoring of genetic markers, reproductive health and developmental outcomes allows for early detection of potential issues. When necessary interventions such as targeted treatments or controlled genetic adjustments are applied to prevent long-term degradation of population viability. These systems operate with the goal of preserving functional diversity while minimizing harmful genetic accumulation. Social structure within the population also influences genetic and demographic stability. Patterns of family formation, resource allocation, and community organization affect how genetic traits are distributed across generations. In a closed environment, social behavior becomes indirectly linked to biological outcomes, as population structure determines long-term genetic trajectories. Stability therefore depends on both biological regulation and social equilibrium. The absence of external migration means that all genetic diversity must originate from the initial population, and any controlled genetic repositories maintained within the ship. These repositories act as long-term biological archives, preserving genetic variation that can be reintroduced if necessary to restore balance. This system provides a safeguard against extreme loss of diversity, ensuring that recovery remains possible even after extended periods of isolation. Over long timescales, subtle changes in population structure accumulate. Even small biases in reproduction survival rates or social grouping can influence genetic distribution across generations. These changes are not immediately visible, but become significant over centuries and millennia. The population gradually becomes shaped by the constraints and conditions of the ship itself, rather than any external environment. Psychological and behavioral adaptation also influences demographic stability. In a closed system, cultural norms and behavioral patterns evolve in response to long-term isolation. These patterns affect family formation, cooperation, and resource sharing, all of which indirectly influence population structure. Stability depends on maintaining functional social systems that support both individual well-being and collective continuity. Despite these constraints, the population remains biologically active and capable of gradual change. Evolution does not stop but proceeds within a narrow and controlled framework, defined by environmental stability and limited variation. The result is a population that is both stable and slowly shifting, shaped by internal dynamics rather than external pressures. The generation ship thus becomes a self-contained evolutionary environment, where human continuity is maintained through a combination of genetic management, social structure, and environmental control. Survival across generations depends on balancing change and stability within a closed system that must remain functional over timescales far exceeding individual human lifespans. The generation ship now reaches its deepest internal layer of continuity, where long-term survival depends not on physical systems alone, but on the persistence of cognition culture and collective meaning across many generations. In this isolated environment, human experience becomes shaped by the absence of external reference points, as no planetary horizon, seasonal cycle, or natural ecosystem exists to reset perception. Instead, continuity is preserved entirely through internal systems of learning, memory, and cultural transmission. Cognitive stability is supported through structured environments that maintain consistent sensory conditions. Lighting cycles, spatial organization, and environmental cues are carefully regulated to provide predictable patterns that allow the human brain to maintain orientation over time. Without these consistent structures, long-term isolation in a closed environment could lead to disorientation or fragmentation of shared perception. Stability, therefore, depends on the repetition of familiar patterns across generations. Memory systems extend beyond individual human cognition into distributed archives that preserve knowledge across centuries. These archives store technical information, historical records, biological data, and environmental logs, forming a continuous record of the ship's existence. They ensure that knowledge is not lost when individuals pass away, allowing each generation to inherit a stable foundation of understanding. This accumulation of memory becomes a defining feature of life within the vessel. Cultural transmission plays a central role in maintaining continuity. Language, customs, and shared narratives evolve gradually within the closed environment, adapting to the constraints and conditions of life aboard the ship. Over long periods, cultural patterns may shift subtly, reflecting changes in population structure, environmental stability, and technological reliance. Despite these changes, core functional knowledge remains preserved to ensure operational survival. The absence of external societies means that culture develops without external influence. This leads to a form of internal cultural evolution, where traditions are shaped entirely by the needs and experiences of life within the vessel. Rituals, communication patterns, and social structures gradually adapt to the constraints of enclosed space and continuous dependence on engineered systems. These adaptations are slow but persistent, accumulating across generations. Psychological resilience becomes essential in maintaining stability across long durations of isolation. Humans within the ship experience life entirely within a confined system, where all sensory input originates from engineered environments. Over time, the mind adapts to this condition, constructing internal frameworks that allow meaning to persist without external reference. Stability depends on the ability of cognitive systems to integrate repetitive experience into coherent long-term understanding. Education systems ensure that each generation inherits not only technical knowledge, but also an understanding of the ship's purpose and functioning. This transmission is essential for maintaining system integrity, as operational knowledge must be continuously renewed. Without structured education, critical systems would degrade as knowledge gaps accumulated over time. Education, therefore, becomes a central pillar of survival, linking biological continuity with technical maintenance. Identity within the ship evolves in response to long-term isolation. Individuals and communities form their sense of self within a closed environment where all external comparison is absent. This leads to identities shaped primarily by internal structure function and social role rather than external cultural reference points. Over generations, identity becomes increasingly tied to the vessel itself as the defining context of existence. Time perception also changes in a closed system. Without natural cycles such as seasons or planetary horizons, time is measured entirely through artificial systems. This creates a structured but abstract sense of duration, where continuity is defined by internal processes rather than external environmental change. Over long durations, this can influence how events are remembered and how generational transitions are perceived. Despite the extreme isolation, human cognition retains adaptability. The brain continues to interpret patterns, form relationships, and construct meaning from available stimuli. This adaptability allows psychological systems to remain functional, even in environments far removed from natural evolutionary contexts. However, this adaptability must be supported by stable external structures to prevent long-term cognitive fragmentation. The ship itself becomes a symbolic and functional centre of existence. It is not only a physical environment, but also the defining framework through which reality is experienced. All knowledge, memory, and cultural meaning are ultimately anchored to the vessel's continued operation. This creates a unified system in which survival, identity, and understanding are inseparable from the integrity of the ship. Over extremely long timescales, continuity depends on the balance between change and preservation. Too much change would disrupt stability, while too little would prevent adaptation to gradual system shifts. The ship maintains this balance through continuous regulation of environmental, biological, and cognitive systems. This ensures that life remains coherent even as subtle transformations accumulate across generations. In the deepest sense, the generation ship functions as a self-contained world where survival is defined by the persistence of interconnected systems of matter, life, and thought. Its existence depends on maintaining equilibrium across physical, biological, and cognitive layers, each reinforcing the others in a continuous cycle of stability. Within this enclosed reality, humanity persists not as a static state, but as an ongoing process of maintenance, adaptation, and continuity, extending far beyond any single human lifetime.